So that's a topic. I don't want you to spend a lot of time on this topic. As long as you know it, you're not going to have a question in your exam, but you need to be familiar with this topic, and it's very, very simple. But let's say what it is. So the title in your textbook, you're going to see it in chapter 4. It's called Indeterminate Problems, or Statically Indeterminate Problems. What does that mean? Let's say I have a bar like this one, and I put it between two walls A and wall B, and I fix it there. And let's say I apply load, maybe let's call it load P, to this connection of these two pipes or whatever it is. And by the way, this connection, we call it flange, like when these two portion A and portion B, we weld them together with a flange, or maybe we screw them or glue them together, right? We apply load P at this flange. So we want to know the stress on each section. We want to know what is the stress here, what is the stress on the section B. So to find out the stress, we need to know, if we apply load P, how much load is on the wall B and how much load is on the wall B. So we can start with the free body diagram, and we say common sense, if I apply load P here, then this wall B is going to have a reaction to the left, and also this portion A is going to have a reaction to the left as well, because imagine when you apply the load P, these things want to prevent it from moving, right? But it doesn't matter if you know the direction, as long as we know that this is an axial load. Let's call these two loads A and B. This is load A and this is load B. From what we've learned so far, we know that sum of the force in X direction must be 0. So we say in X direction, we have P, we have minus A, and we have minus B equal to 0, right? So let's say we know this P. It is now, it's 100 kilogram, 10,000 Newton, or whatever. But we see with this formula cannot help us, right? Because it has two unknown. We use other formula that we know. We know that there are 3 formulas. Sum of the force in Y direction must be 0, but it's not useful really. Not useful. What about taking a moment? The same, it's not useful, right? When we take a moment, again, all of these forces are in one line, and these 2 formula cannot really help us. So we are stuck with just one formula, like this one, but 2 unknown. These type of problems, they call statically indeterminate. They are not determinate. We cannot figure them out by just using what we learn in a static. So we have to use other tricks to solve these problems. And the way we solve these problems is like a simple trick. The way we do it, we say, well, assume that this wall B is gone, it's not there. So assume, to solve this problem, let's say, to solve this problem, imagine that there is no wall B. Imagine there is no wall B. If that's the case, then we know that something is going to happen to this section B, right? Let me draw it like that. Okay. So if there is no wall, then we know because of this load, this portion is going to elongate. Let's call this amount delta. And we can calculate delta. We know, well, this delta, if I apply load P to this flange here, to this connection, right? So this portion B, basically there is no force on it. Imagine there is nothing here, right? There is no wall B, there is no force B, it's nothing. It's just this portion is sticking out, it's free. So this load P is just extending this portion A. So delta is going to be then PA over AE. Remember the general formula that we have? I'm just writing out at the top, FLAE. And here the force P is applying only on this portion, on this section. So, but we know that in practice we have this wall. This is just something we imagine, right? And so we know that, let me draw it again. This B has to compress everything's back. But because of the wall B, there is a compressive force B try to push the bar back, right? So there is this force B here, try to prevent this delta. And how much power has this force B? Well, we know that if I apply load B, it's going to be a delta equal to force B. We don't know how much it is. And now this time this force P is applying to the whole length, right? The whole thing's L. Because this load B tried to compress the whole thing. Area is the same, modulo of elasticity is the same. So these two has to be equal because we have a wall here. There shouldn't be any delta. So this delta that we imagine in Formula 1 has been canceled by delta that we calculate in Formula 2. So if I say they are equal, PAE equal to BLAE, from here I can find out that B is equal to P, and instead of L I can put A plus B multiplied by, yeah, that's the answer, right? So we found B, that's good. And we have another formula over here, right? If I use like formula 3, and from 3, we can find A as well. Because this is B, I substitute it in formula 3, and I can find A, which is, oh, here we have to be careful. We have like, I guess we have another A here. Yeah. BA plus B multiplied by P. Okay. Let's double check it together again. I substitute L by A plus B, and I can find B here, like AE cancelled by AE here. Yeah, that's correct now. B is PA divided A plus B. I substitute this number here for B, and I can find A, right? So you see, this is the way that we can solve a problem that is not determinate statically. We try to remove one of the support and see how much it extend or deform, and then using this basically formula, we can find out the reaction. Any question?
Yeah, I'm a little bit confused how we set the PA over AE equal to BL over AE at the bottom. I just got a bit distracted.
Okay, yeah, I'll explain it. Thanks, Oliver. So, so Oliver is asking how come we said 1 is equal to 2. Let's go back to the method that we solved this problem, right? So we made an assumption at the beginning, or we imagine, not an assumption. We said that imagine there is no wall B. If there is no wall B, then we know that because of this load P, this bar is gonna stick out, like how much? This delta, right? So far good? So it's gonna be PAAE. So that's this portion. But we know in practice, this is just our imagination. This is not what we have, in fact. What we have is this big wall B standing there with a force B and preventing everything from preventing this delta from happening, right? So and then we said, well, this B has this power, BLAE. Imagine we don't know if it is delta. Let me remove this one. Right? We know this B has this power to compress everything's back. How much? BLAE. So far we are good, Oliver?
Yeah, so far so good.
Okay. Now we said, okay, this is our imagination. Because there is this wall B, then this delta shouldn't be there. Whatever this delta is, wherever it comes from here, it must be canceled by this B. So this B has this power, this amount to compress it, and it has to cancel this one. And that's the reason I said 1 and 2 must be equal. Is it clear now or no?
Okay, so we're saying the amount that B compresses cancels out the amount that A expands?
Exactly. Yeah, this is what we say, and that's why we say these two has to be equal. Otherwise, they are not compatible, right? We say
Yeah.
otherwise we said, okay, if there is such a case, let's imagine this wall B is a flexible wall. It's more like soft Dow shape, right? Then if you apply the load, B is gonna go inside the wall. But if this wall is a, let's say, steel, concrete wall, it's not gonna move, then it has to be canceled, and so these two has to be equal.
So in the bottom equation where we have PA over AE, that P, does that refer to the actual force P that's being applied in the middle, or is that the force that is acting through A?
No, that's the force actually apply in the middle here, P.
Okay.
This P.
Okay, thanks.
Yeah, try to think about this again, and I'll try to solve another example for your tutorial, so hopefully it becomes more clear. All right, if there is no question, let's move on to a new topic. Again, as I warned you at the beginning, module 2 is a little bit hectic, lots of new concepts, but don't worry, we'll use them a lot and a lot. This is just the beginning, which we introduced them. So what is this one? Hooke law for 2D problems, right? Let's step back and see what was the Hooke law in the first place, right? So we said in the first place, if we have something, let's say a simple bar like this one, something that we can consider it as a 1D problem, like maybe a long bar, more like the cable that you saw for the elevator, which is the length is compared with the diameter is very, very large, and you can assume it is a 1D problem. So in a 1D problem, you saw that if you apply an axial load, there is going to be a stress and a strain, and there is a relation between a stress and a strain, which we simply said sigma is epsilon E. And this is what we call it a Hooke law for 1D problems. So now imagine that we are dealing with a problem that is, we cannot assume it's 1D. It's more like a plate, right? And let's call this one, it's a 2D problem. And this one is like a bar or a link or something, and this is a plate. And in this basically setup now, imagine that you are applying a stress in both directions, in maybe X direction and also in Y direction. And by the way, like here, I'm showing only tension, like tensive loads, or when the thing is under tension, but the same concept, right? When it is under compression for this bar or here, we just need to be careful for the sign, okay? So in this scenario, let's call this direction X and the vertical direction Y. So this is X and this is Y. So let's think about it for a moment. If you apply load in X direction, okay, we know that something is going to happen in Y direction, right? And this one was because of something that we just learned. It was because of Poisson, right? If you apply load in X direction, something is going to happen in Y direction. So it means when you have load in X and in Y direction, the strain in X or Y is not just because of the load in X and Y. It's because of combination of these two. And this guy Hooke proved again another formula for us, which the proof is in your textbook, but we don't need to study the proof. We just use the formula. It says that the epsilon in X is equal to 1 over E, or let me write it down like that one, sigma X over E. So this is sigma X, this one is sigma Y. This one is so far is very similar to the one that we can see over here, right? You see the 1D formula? You can write it as epsilon is equal to sigma over E, right? So epsilon X is sigma X over E in X direction. But we know that this sigma Y also is going to have a role. It's going to play something here. When you apply this sigma Y, what will happen? The length in X direction is going to increase or decrease. Imagine if I stretch in Y direction. What's going to happen, Thomas, when I apply this sigma Y?
It's going to change the sigma X inversely.
What's going to happen to the size in X direction? What's going to happen to the strain in X direction?
It's going to shrink down, I think.
Exactly, it's going to shrink down. That's correct. So my question was, when I'm applying this sigma Y, right, what happens in X direction? As Thomas said, it's going to shrink, right? So it's going to be then minus. How much is going to shrink? This is something that we learned from Poisson. It is Poisson multiplied by basically epsilon in Y direction, which epsilon in Y direction is sigma Y divided by E. Again, this is the proof. You don't need to know the proof. You just use the formula. I just write it down so you know where this actually comes from. So let me simplify it. Epsilon X is equal 1 over E sigma X minus nu sigma Y. And with a similar concept, we can write down epsilon Y, which is 1 over E sigma Y minus nu sigma X. And this is something we call, this is something we call Hooke law for 2D problems, all right? And don't forget these sigma X and sigma Y, when you substitute them, when you use this formula, when you substitute them in this formula, you need to consider their sign. If they are compressive, you use a negative sign. If they are under tension, they are positive. Okay? Is there any question for a Hooke law for 2D problem? Are we good? Okay. Now that you are good with 2D problem, let's make it more complicated, right? Let's deal with a Hooke law for a 3D problem. Let's imagine that instead of a plate now, you have a cube, and this cube is under stress in 3 direction, X, Y, and Z direction, basically. And the question is, we want to know how much this cube is going to shrink or elongate because of these stresses. And again, I show just a tensile stress. It can be compressive as well, which is the same formula. Again, we don't need to know the proof, but this is the Hooke law basically for a 3D problem. Epsilon X If you can hear a voice, it is a construction, or maybe, no, sorry, it's just a try. So it is epsilon x is 1 over e sigma x minus nu sigma y plus sigma z. Sorry for my handwriting. And epsilon y is 1 over e sigma y nu sigma x plus sigma z. And epsilon z 1 over sigma z minus nu sigma x plus sigma y. Let me quickly I need to find out. Okay, let me quickly close my window so it's too noisy here. Sorry, I come back. Okay, it's better now. All right, and this is another set of formula which you guys need to know, and it is known as the General Hooke law, because that's for the most general case, which is basically a 3D problem. Question for this one? It looks a little bit complicated, but this is just a simple formula. When we deal with a problem, we just use it and we substitute the numbers. And again, I'm going to solve problem for you so you could see how you can use this one.